Okay, so welcome back to the second session this afternoon. So the first speaker is named Harman, and he will talk about some representations of special linear groups. Please.
Great, thank you. Right. Okay. So I'm gonna use my 15 minutes a little bit different. I'm gonna probably spend most of it giving a sort of some exposition about a result from 1960s. That's obviously not mine, but it's a result I really like. But moreover, it's actually not really the sort of thing that I typically work on. However, at the end, I'm going to explain, at least sort of state a result of mine, kind of generalizing it to a setting that I do think about a lot, hopefully giving a flavor for kind of the type of things I like to do. Okay, but so I'm going to talk about some representations of special linear groups, and you might be wondering what I mean by that. I could mean kind of a lot of things. It's a vague title. So I'd like to start off by sort of clarifying actually what the setting is that I'm going to be talking about. So first of all, I'm going to the word representations. So for right now, I mean, I have a group G, and it's acting on a complex vector space by linear transformations. So kind of the most usual thing that people think of when they think of group representations. So in particular, I am here for this special year on geometric and modular representation theory, but the stuff I'm talking about today is sort of decidedly not geometric or modular, but I think it's cool, so I want to talk about it. Okay, so that's what I mean by representations, and I also want to clarify what I mean by special linear group, because I could mean a lot of things by that. And what I'm interested in today is SLNZ. So this is the group of n by n integer matrices of determinant 1. And moreover, I'm sort of particularly going to be interested in SL infinity Z, which I'm just taking to be the union of those groups. So SL2 sits inside SL3, sits inside SL4, and you can just take a union of them. So if you like, you can think of it as like infinite square matrices, which differ from the identity matrix in finitely many positions and satisfy this determinant 1 condition. So those are the special linear groups that I'm interested in. And maybe I'll just say that these kind of infinite rank examples is really kind of the setting that I think about a lot. So for today, I'll be talking about SL infinity Z, but I also think a lot about kind of the infinite symmetric groups, infinite general linear groups, braid groups, that sort of thing. So that's maybe what like a common thread in my research, but for now I'm going to be talking about SLNZ a lot. But all right, so I've clarified what I mean by representations and what I mean by special linear groups for today. I'm going to clarify the word sum in the title, so there's some representations of special linear groups. And what I mean by that is for SLNZ, where n is finite, I mean finite dimensional representations with sort of no further restrictions. And for SL infinity Z, I'm going to mean a class of representations that I call admissible representations. So I'll say a bit about what this condition is and where it comes from later, but ultimately it's going to be some sort of finiteness condition to impose on representations of SL infinity Z, because, well, for one thing, that group has no finite dimensional representations, I guess, other than the trivial representation. So it's some sort of finiteness condition on representations of SL infinity Z. All right. But so to start, I want to talk about the representation theory of SLNZ. And so to start, I want to sort of talk about sort of two ways that you might construct complex representations of SLNZ. Two ways that you might try to do it if you're sort of like me and have a kind of background in representation theory. So the first kind of easy source of representations of these groups are what I'm going to call algebraic representations. So I just take SLN Z, this kind of infinite discrete group, and I just sit it inside SLN C, or if you rather SLN R. And then I can take a representation of SLN C and restrict it to SLN Z. So in particular, though, SLNC is a very nice group. It has lots of extra structure. It's a say semi-simple algebraic group or a complex Lie group, and we can talk about representations of it as an algebraic group or as a Lie group, where we care about kind of not just representations of it as an abstract group. So in particular, I'm going to talk about kind of algebraic representations of SLNC, which, if you're more analytically minded, is equivalent to just being a holomorphic representation of SLNC. And I can restrict those to SLNZ, and that gives me a bunch of representations. Great. So that's one easy thing I can do. Another thing I could do is I could take my n by n integer matrix and just reduce all of its entries mod m for some integer m. So this reduction mod m is a homomorphism from SLNZ to SLNZ mod mz, and in fact it's surjective. So then in particular, I can take a representation of SLNZ mod m, which is just a finite group, and I can kind of pull it back to SLNZ to get a representation of this this much larger group, this infinite discrete group. Right, and kind of the benefit of these two methods of producing representations is, well, we know a lot about the representations of SLNC. We kind of have all the tools of, Lie groups and algebraic groups for that case. And we know a lot about representations of finite groups. And in particular, SLN Z mod M is fairly well studied. I mean, certainly if M is prime, we know a lot about these representations. And there are some interesting questions still about powers of primes. But it's, in both cases, it seems much more tractable than the starting problem for SLNZ. Okay, so these are two kind of nice, almost obvious constructions of how you might produce representations of this group. Now I want to state a theorem from the 60s, classifying the finite dimensional representations of SLNZ. So this theorem, I don't quite know how to attribute it. I think the version I'm going to state kind of first appears in the work of Steinberg, but he's drawing heavily off of paper by Bass, Milner, and Sayre, and kind of the case that I'm actually talking about today, where it's SLNZ itself. Really, the key kind of ingredient originates in a paper of Meneke. So I don't really know how to attribute this, but this was all worked out in the 60s by various people. Anyway, so the theorem is the following: for n greater than or equal to 3. So first of all, the finite dimensional representations of SLNZ are completely reducible. They decompose as direct sums of irreducible representations. So if you're not a representation theorist, you might think this is kind of a usual feature of representations, in characteristic 0 at least. But I would say this is something you would expect for, say, for finite groups or compact groups or maybe reductive algebraic groups, but definitely not for infinite discrete groups. So this is kind of surprising in its own right. But moreover, we can classify the irreducible representations. And every irreducible representation, V, factors as a tensor product, V alg tensor V fine. So an algebraic part and a finite type part. So the algebraic part is something that's coming from SLNC, and the fine part is coming from SLNZ mod M for some M. And so every irreducible representation factors this way. And moreover, this factorization is essentially unique. So if I have two such factorizations of an irreducible representation, I can match up both the algebraic part and the finite type part, and they have to be isomorphic as well. So this sort of completely reduces the finite dimensional representation theory to those two special cases that I mentioned before. So kind of all you can do is those constructions and then tensor products and direct sums. All right, so this is, I think, a beautiful theorem from the 60s. I should give a warning. This is wildly false when n is 2, and it's false for infinite dimensional representations as well. So for n equals 2, representations are not semi-simple. They don't. There are interesting extensions between them, and moreover, they don't have this this kind of tensor product decomposition. And then for infinite dimensional representations, kind of it's as wild as possible. So kind of nothing nice can be said in that case. All right, but that's in a sense the classification of representations of SLNZ. So now I want to go to kind of my setting, this infinite rank setting, and say a bit about what I do. So I mentioned there's this class of representations called admissible representations. I gave it that name, but it's really coming from something called representation stability. And representation stability is a sort of theory that has arisen in the last, I don't know, 6 or 7 years. It's actually coming out of geometry and topology. So they've kind of found sequences of representations of kind of families of groups that are related and give nice stability properties. But maybe the important part of it is that they're sort of appearing in the wild. These are representations that are appearing, in geometry and topology. But this condition, this admissible condition, is sort of what we get on the stable part of a representation stable sequence. Anyway, so to roughly say what this condition is, I won't go into details, but at least to say what it is roughly and kind of motivate calling it admissible, it's characterized by a couple of properties. So first of all, vectors in these representations have big stabilizers. So there's some class of subgroups that I'm thinking of as being big, and every vector has to be fixed by one of them. So these behave sort of like an open neighborhood of the identity, if you like, p-adic groups. And then on the other hand, these big subgroups that I have, they don't have too many invariants. They have finite dimensional spaces of invariance. And so this is sort of very analogous to the notion of admissible representations for p-adic groups, which is kind of why I chose that name. And I'm also going to consider a finite generation property. This could be relaxed, but it's important. It's an important condition in representation stability. So I want to kind of include it in my definition. All right, so I'd now like to just state a theorem of mine kind of in this setting. So here's the theorem. So first of all, admissible representations of SLN or SL infinity Z have finite length. So they're not necessarily a direct sum of finitely many irreducibles, but there's at least sort of finitely many composition factors. All right. And then looking at an irreducible piece, we again have a tensor product decomposition. So an irreducible representation, admissible representation of SL infinity Z is a tensor product of an irreducible admissible algebraic representation of SL infinity C and an irreducible admissible representation of SL infinity Z mod MZ. So we have the same sort of tensor product decomposition. And finally, it's again unique. This gives a sort of complete classification of the irreducible representations in this family. And yeah, I think that's my time. So thanks for listening.
Wow.
Can I make a semi-historical remark of an old guy who remember things? The theorem that you quoted of Menneke and Bas-Milnor-Serre, etc., is a very cute way to express it in one-line equation, saying that the so-called Orshil-Mosto completion, or it used to be called, or maybe the pro-algebraic completion of SLNZ, is SLN-C cross SLN-Z hat, the profinite completion of Z. Without knowing your definition, I have the feeling that maybe, so, and this half-aligned statement is equivalent to this theorem. It's completely equivalent because it's a product of two groups and every reducible representation is a tensor product. I wonder if there is such a categorical object that you can associate with SLN with the admissible representations of such a group like SLN infinity, which will be probably SL infinity of the complex number cross SL infinity of Z hat, and this will be kind of a conceptual way to state your theorem. I mean, I'm not claiming this is not going to be a magic tool to prove the theorem, but I think it gives kind of conceptual a feeling what is and suggests very much what should be the generalization.
Yeah, I agree, and I sort of have thought of this this formulation that you said a lot. I think making it precise is more subtle. There's I don't think it'll be kind of this product on the nose as you mentioned. So it's a little more subtle, but absolutely, I've been looking at.
If I give you just a group gamma and I'll ask, just like the pro-algebraic completion is defined in a completely abstract way, in a categorical way, is there a way to associate with a group a categorical object that will represent the admissible representation?
That's a really great question. I don't know. Right. So doing this kind of pro-algebraic completion, you're sort of running kind of this Tanakian formalism,
yeah.
and kind of the problem is these infinite dimensional representations are not kind of Tanakian categories. You kind of don't have this strong notion of duality that you require, and you don't have a nice fiber functor to finite dimensional vector spaces. But morally, it feels like there should be something there. This admissibility condition is sort of some approximation of a finite dimensionality condition. And so, I'm hopeful that something like that can be done, but I don't know yet.
Okay, we'll discuss it privately, but just last sentence, there is a way which was defined by Grothendieck, who defined this, I mean, it didn't define for that, but it's equivalent. It take all the automorphism group of the forgetful functors, commuting with tensor products, very abstract, which is really give you this pro-algebraic. I wonder if this can be a formulation that may suit you. I just suggesting something.
Yeah, let's talk more.
Yeah, pleasure.
Related question, is the tensor product?
I have a quick question.
Okay. So who's going to speak first? I mean, I guess Pierre actually started already, Peter. Can you wait?
So, is the tensor product of two admissible representation admissible?
Yes, although that's not immediately obvious, and there might be a sort of caveat. There is a natural tensor product on them, and it's not obvious. This condition is a little funny. I mean, I'll say that for maybe just the admissible representations of SLN-C, so sort of ignoring the finite type part, it's like you take the matrix representation. So there's a sort of natural representation of SL infinity C on an infinite dimensional space. There's a sort of restricted dual version of that where you act by the inverse transpose. And then if you just take tensor products of those two representations and take all possible subquotients, those are exactly the admissible algebraic representations of SL infinity C. So it's closed under reasonable, tensor products and things like that.
Is there any relation to the work of Olshansky and people like that, where they do this with classical groups and take this limit and look at its representation theory? Do you know?
I don't know. I'm not sure I'm familiar with that off the top of my head.
It gives sort of statistics then on Young tableaus, all done sort of going through this limit in this inclusion, similar to your inclusion, but it's of course not it's a much simpler group than SL and Z. Anyway, sounds like there's a lot of interest here.
Single question.
Yeah, just a small question. Is the tensor product VL tensor VFin always irreducible?
Yes. Yeah, well, if you start with two irreducible things, then the tensor product is irreducible. Yeah.
So if you wanted to understand extensions between irreducible representations, is it true that they're all explained by extensions between the factors?
That's a really good question. And that I think actually is closely related to the question that Professor Lubotsky brought up of to what extent this is kind of a genuine product or some sort of pro-algebraic completion of it is a product. It seems like it's a little bit more subtle than that. I can't really go into it right now, but it should at least be maybe morally true. They should be coming from those, but maybe not literally in kind of the most naive way you would think.
Actually, can I just, so I seem to remember this there's also this Bass-Milner-Serre result also applies to the symplectic groups. Is that correct? And I was just wondering if you'd looked at generalizing your result. Can you do a generalization of your work to the symplectic case? Or? Yeah,
so the symplectic case, so if I look at SP2 and Z, I haven't gone through it in idea, but I think everything goes through essentially as is. A more, also in Bass-Milner-Serre is they consider other number rings, and that direction seems much harder. So I'm sort of currently doing that, and there are a lot of kind of things that hold for the integers that really simplify the situation from the general number ring setting. So I've sort of been spending the last 6 months or so trying to upgrade this to other number rings, and it's there are a lot of kind of interesting subtleties in that direction.
Okay, so I don't want to hijack the lively discussion, but we still have 2 other people to actually listen to. And so thank you